Okay, I'm going to be talking about convolutional neural networks today, and they've become really popular for all image related tasks these days. In fact, many of the non image related tasks also can leverage convolutional neural networks. They have some certain really interesting properties which make them very useful. But before going into the specifics of convolutional neural networks or CNNs in short, I'll be talking about the kind of things which led to CNN becoming very useful. Guess you might have heard about this challenge called Imagenet. It's a very popular computer vision challenge released by Stanford, which has 14 million images, 20,000 categories. It sounds very rosy about, there is a challenge, there is computer vision research going about trying to beat the previous year's approaches in this challenge. But the project had very humble beginnings, and which I think are really important to put into context, and also to sort of celebrate the effort done by some of the people working towards this challenge. And there is a really interesting article which I've linked over here, which says that ImageNet is the data that transformed AI research and possibly the world. And this, you should try to read the article. It gives a lot of really useful insights. I'm anyway presenting some excerpts from the article. The article says that in 2006 or so, the AI or computer vision or machine learning community was largely focusing only on algorithms. So everyone would want to propose a better, more complicated, or more sophisticated algorithm to make better decisions. But no one was talking that much about data. At least this is what the article suggests. But Feifei, who was the pioneer behind Imagenet Challenge and a lot of really amazing computer vision and deep learning work, she said that the best algorithm would not work if the data was not representative of the real world. And there were serious repercussions to their project, and we just looked through it. And so they decided that they want to do something about it, and they wanted to map out the entire world of objects. So this is humanly impossible when you talk about the entire world of objects, but of course with some boundaries, some limitations, you can still do something like this. And this is where the concept of ImageNet was born. And this ended up being published in 2009 as a research poster. So for those who do not know, many of the leading computer vision, machine learning, data science conferences have spotlight presentations, which are a really small subset of all the chosen papers are allowed to give an oral presentation. The other presentations, the other papers, even though the full papers are generally presented as poster papers, so this paper was also sort of uh, not received with the with all the set of with all the appreciation that it should have been. And this sort of was just one of the many hundreds of posters stuck at the corner of the conference, and would have probably got lost in that noise. And Fifidi said that a lot of people were paying attention to models, but they suggested that they should pay attention to data as well, and data will be defining how we're thinking about the models. So what is really interesting about ImageNet is how it's really inspired from a different domain, and that domain is sort of trying to map all the words in the English dictionary in a in a sort of a hierarchical representation. And this is an old project. So this was in 1980s when a Princeton psychologist started a project. The aim of building a hierarchical structure for the English language, where the hierarchical structure means that a dog is a canine, but a canine is a mammal is an animal, and so on and so forth. So they were trying to create this hierarchical structure for the entire English language, and this. So I think they ended up doing more than 150,000 words. And now coming back to ImageNet, Fairfield said that in this article, she said that previous data sets did not really capture the complexities of the world, and the idea was that if you had seen a lot of pictures of certain animals, etc., or of a certain object, you could do much better than just having a really lab setup kind of an environment of data set or really small data set. And this is where I think a lot of us should also pay heed to that. Safely took inspiration from WordNet. So this is a very different. If you don't think through it, you'll see that these vision task and let's say natural language task may not appear to be exactly coherent, but she took some inspiration from the hierarchical structure and organizing the WordNet project, and she thought that could be associate something more even with the computer vision like tasks. And the start of the project was not going well because they were trying to hire undergraduate students for $10 an hour to manually annotate images and find the images. But they then also did some calculations and figured out that it would take 90 plus years to create the kind of data set or the scale of the data set that they plan to do. So this was not going to work out. And this is sort of both the sad thing and also the happy thing that Fefili pulled through and has become one of the leading scientists. That so the undergrads she felt were time consuming, the algorithms were flawed. So Fefili was also not winning any grants, and you need grants to sustain as a faculty to pay your research staff, etc. And some of her comments were really condescending. And this is again a really hero story to see how she's pulled through and how eventually everything, uh, you know, now the ImageNet is seen as one of the most important things in the AI world. And this was another interesting thing that happened, that when she this is mentioned that in a conversation with a graduate student, Fefili was that student introduced her to Amazon Mechanical Turk, where I don't know if how many of you've used it, but I've used it. You basically give some tasks and you're crowdsourcing your way to completion of that task. So you could pay, let's say, half a dollar for annotating 20 odd images. This, of course, comes with its own cost, that the labels will be noisy because these are not experts who are labeling, but you get a scale. So this is how they quickly changed the system, allowed. So they basically brought in Mechanical Turk, Amazon Mechanical Turk into it. But then they said that even after the Mechanical Turk system was integrated, they took 2.5 years to complete. So to put this into context, many of the research projects are, you know, a lot of people would have ridiculed this group that what you're doing is not even research, this is pure engineering, or this is useless stuff. You should instead focus time on creating more sophisticated algorithms, so on and so forth. But again, I think this is an inspiration in terms of looking at how their group was resilient and how they stuck to the task and had enough faith in going ahead. And they finally labeled millions of such images. And then they, in 2009, they published the Imagenet paper. And there also, Fefili was says in the article that people are still skeptical of the idea that more data is useful. Of course, now when we circa 2020, when we revisit this line of thread, it is very obvious that data is one of the most important things to have revolutionized a lot of these algorithms, availability of data. And if you look at the ImageNet challenge, this the numbers are also very stark. So in the initial few years, most of the teams were in the ballpark of 50% accuracy, more than 50% wrong. And in 2012 was the year when deep learning was first applied by Jeff Hinton and group. So uh, this is just to say that in many cases, Feifeli and many of her colleagues and so many people who've put in so much of effort also need to be always sort of their achievements need to be explained well, because without the data many of the deep learning algorithms would not have been useful, and eventually you've seen that the errors are keep creeping low, and 2017 or so most of the teams were fairly accurate. And coming to the coming to this specific paper in 2012 from Jeff Hinton's group, this paper was called AlexNet. The first author, I think the first author has a first name of Alex. And if you look at this sort of complicated looking diagram, this is for those who have already seen what are called convolutional neural networks. This is fairly simple to understand, but this looks fairly big, something going on. But the interesting thing is that this particular network is not very different from a network for convolutional neural network that was proposed by Jan LeCun in 90s. So what changed between 90s and 2012? It is mostly that the data set which was available, and secondly the compute power became readily available. And I think another interesting point and a historical point was that I believe this was Andrew Ng's group who first proposed, I'm not fully sure about this though, Andrew Ng's group who first proposed using GPUs for machine learning and for sort of tensor operations and machine learning and so on and so forth. But before that, uh, this was not done it regularly. So all of the recent success is basically a combination of so many factors, and the important thing in this particular slide that I wanted to show was that a lot of the research, while we think is very new, but circa 98 Jan LeCun was processing so many checks through this convolutional neural networks. And the AlexNet architecture is not very different from the architecture proposed by Jan LeCun, and this net is generally called is called LeNet. Okay, so having studied the history and having studied the Imagenet challenge and having got some context of why we are talking about convolutional neural networks, let's now do a dive into some of the methods involved in convolutional neural networks. An important thing I want to upfront make clear that we'll not be doing a lot of convolutional neural network stuff. We'll just be looking at the basics. I hope that if you're really interested, you will pick up relevant literature and relevant articles and read into more. Given the limitations of time and the other topics that we also have to cover, we'll probably not go super deep into convolutional neural networks. And at the end of the day, this is a machine learning course and not just a neural network course. So we'll now talk about modern day cameras. So that's another thing which has really revolutionized computer vision task, which is and machine learning and for image recognition task, is the availability of camera now in almost every hand. And I think there are reports which suggest that this specific report suggests that the Apple camera or the iPhone camera is the most popular camera in the world across all brands, across all types of cameras. So this tells you a lot of things, that a lot more photographs are now being clicked than they were ever before in the previous 2 decades. Let's try and understand that what is the camera size or the photo size have to do with neural networks, etc. And why do we even need convolutional neural networks when we've already discussed something like multi-layer perceptrons, which are also fairly accurate in a lot of tasks. So let's look at the specific camera from Xiaomi, this specific phone with this 108 megapixel penta camera. So you'll keep seeing these big words like 108 megapixel, 48 megapixels, so on and so forth. Let's try and now create a neural network to do a very multi-layer perceptron to do a really simple classification using images obtained from such a camera. So let's see how suitable an MLP is, and what I'm going to do is let's assume that this is the image taken by the camera itself. Now this will contain some height and some width, and then there'll be a third dimension which is for the color, so RGB. And what I say is that we'll just flatten out all of these numbers, so height times width times 3, and just flatten it out into a vector, right? So something like you put this first, the second pixel, third pixel, so on and so forth, and then the second row and all the columns, and then across colors, etc. So once you've done that, you flatten this out, you'll get an input layer, and for the purposes of simplicity, we'll connect it to a single hidden layer only, and then there is an output layer, right? And what we're trying to do is to classify between cats and dogs, and let's just assume that the hidden layer size is 100, which is fairly normal, nothing huge that way. And what we know is that the number of nodes or number of neurons in the first layer is 100, but the important thing is that the number of neurons in the first layer or the input layer is 108 megapixel, and then you have 3 channels, right? So 108 into 1 million into 3, right? That is billions, that is a vector of more than a billion numbers, right? So n0 is more than a billion, and the size of the weight matrix W1, and let's just assume that each parameter in W is a 32 bytes parameter. So the size of the weight matrix would be at least 32 bytes into some hundreds of billions, which is several GBs, right? Now this is a very trivial neural network that you've built. You just have a single layer with 100 neurons. In general, you'll have a lot more number of layers and a lot more number of neurons in each of the layers. So if you've this should convince you that even for such a trivial task, MLPs are probably not super suitable, because the size of the network involved is huge. And there are other reasons also why multi-layer perceptrons are not particularly suitable. Okay, so you see two images. As a human, can you comment that both of these are cats? Yes, you can do that. Now assume that these are both 100 by 100 images, 100 pixels by 100 pixels, although they are not, but let's, for the purposes of illustration, let's assume that, and look at the bounded rectangles, and assume that the bounded rectangles are 10 cross 10. For some reason my squares are like similar to rectangles, but don't worry about that for now. Now the important thing is that a cat ear will be a cat ear irrespective of whether it occurs, let's say, center and top versus it occurs center and mid, something like that, center and center, right? But the multi-layer perceptron would treat each of them as different features, right? If you remember what the multi-layer perceptron was doing, it was just flattening out all of these pixel values and just stacking them up into one large vector and then feeding it forward to a neural network. So basically this portion will get different weights compared to this portion, but we don't want that, right? We want an ear to be matched to an ear, or weights for an ear to be matched to weights for an ear. So basically what we want is something known as translation invariance, which is to say that the features that you end up which you use should be invariant of translation. So even if you are to translate vertically, horizontally, or rotate or do something like that, your approach should still be working fine. It should be built in order to leverage such factors. The other interesting thing is that MLPs or multi-layer perceptrons will assume that all input features are independent, right? All you're doing is to just stack up all of these pixel values into one large array, but then after that you just assume all of them to be independent. But for images, do we know that two nearby pixels are related? Yes. For example, this image will be closer to this image and so on and so forth. So if you see an white image here, a white pixel here, a lot of the pixel nearby will also be white because of spatial locality and pixels nearby being similar. But MLPs don't leverage that. So that's again something which is not particularly well suited for MLPs to handle images. And the other, then based on these insights, the key idea that we want to build is that we should be looking to build some local feature detectors. So by local I mean that the scope is fairly local, it is not global. So local features could mean you are looking at you're trying to build an eye detector, a face detector, an ear detector, and then you'll do some matching for these individually detected images, or you'll build a network on top of these smaller features. So this is where the whole operation of the convolutional neural networks come into play, and we use something known as the convolution operation and filters. So these are the building blocks for convolutional neural networks, and a lot of my slides for this particular lecture are borrowed from this excellent paper called A Guide to Convolutional Arithmetic for Deep Learning. So you're more than welcome to go through that paper in order to understand some of the things which we are maybe not covering here, or go back and read in more depth. So we talked about building some detectors, right? So building these detectors means that there has to be a way in which you apply some operation on an image, and we are able to get something like a bounding box, or we are able to detect certain kinds of things, right? In general, the easiest kinds of things to infer are edges, vertical edges, horizontal edges, and those who would have studied computer vision or related courses would already know that there are kernels and there are filters you can use to detect certain important, you can detect edges, so on and so forth. We'll be looking at filters and understanding how convolution operation happens. For now, just assume a filter to be a way or a set of numbers which is applied or is used in some arithmetic with the input to get an output, right? To give you more context, let's first look at this filter. You have a 3 cross 3 matrix with values 0, 1, 2, 2, 2, 0, 0, 1, 2, and let's say you have an input. Now, while I've drawn a matrix here, this is in essence an image, right? It is an image of certain number of pixels height, certain number of pixel width, and one channel. So there is only one channel, there is no RGB kind of a system here. The convolutional operation is basically just put those numbers here. So you had the filter as 0, 1, 2, 2, 2, 0, 0, 1, 2, and you multiply. So you do an element wise multiplication of 3 with 0, 3 with 1, 2 with 2, 0 with 2, 0 with 2, 1 with 0, 3 with 0, 1 with 1, 2 with 2, and add up all the entire products. So the final number we'll get is 3 into 1 plus 2 into 4, which is 7, plus 1 8, plus 4 12, right? Now what you do is to now move the filter right. So you move the filter 1 pixel right, and you do the same operation. So 3 into 0, 2 into 1, 1 into 2, 0 into 2, 1 into 2, 3 into 0, 1 into 0, 2 into 1, 2 into 2, and the number you get is 12. And you keep repeating this procedure, and finally what you will get is a matrix like this: 12, 12, 17, 10, 17, 9, and 9, 6, 14, right? I would request, if you've not fully understood it, or even if you understood, this would be good exercise just to try this out on your own and complete the matrix. So you start with the input, you look at the filter, and then you compute the output, and then compare that what you're getting is the same thing as what I put here. Another way to understand, another visual way to understand convolution is Yeah, so the dark blue region that you see is the filter superimposed the input image, and then you see that corresponding to each time the filter rolls over the input image, you get a corresponding number, right? So you applied a filter on an image and you get another matrix. In this case, the matrix is smaller than the input image, which is mostly the case until and unless we do something known as padding, right? There is a notebook that I have on edge detection. I think I can go over that now itself. Alright, so I am showing you a notebook where I have read in an image of our hostels, right? And I've converted that into grayscale. So this is the image in grayscale, looks a little spooky, and I've just done a bit of cropping. The earlier image, the default image was 400 cross 638. I have just cropped it to 400 cross 400, and while I'm using Keras here and I'm sort of applying the Keras convolutional filters, you could have done this in a much simpler way. I have used a 2D convolutional filter, etc. Don't worry about all of the terms here, but the important thing is that I've used a filter of size 3 cross 3, right? And I've also, in this case, I've put the values for the filter. So the filter size, the filter values that I've put is 1 0 minus 1 1 0 minus 1 1 0 minus 1. So those who have taken computer vision would already very quickly understand that what kind of a filter is this, and if you even see the variable name, you might understand what kind of a filter is this. I am then showing you what is the prediction or what is the output that I get on applying this filter on this image, right? So if you remember, I apply a filter on an image, I apply I apply a filter on an image and I get another image. So that's exactly what will happen. I apply this filter 1 0 minus 1 1 0 minus 1 1 0 minus 1 on this image and I get another image. But if you look at this image carefully, you'd see that this image is showing you all the vertical edges, right? It is sort of picking up all of these windows. It is also picking up some of the vertical edges which exist amongst the buildings, etc. And you can also just change this. This should have been a horizontal filter. The variable name should have been changed, and you can just apply a similar filter and you're able to detect the horizontal edges, right? So this is basically showing you, and you can also see this operation being done on an MNIST kind dataset. I'll just skip that for now. This is, you can go through the notebook and understand this concept in more detail. But the high level message that I want you to take from this is that applying these filters allows you to look at develop some features such as edges and more complicated features. At the first layer, you would expect to learn very low level features such as edges. As and when you advance through the neural network, you will probably learn more advanced kind of features. So like you'll probably also look at a combination of vertical and horizontal edges to figure out things like squares and rectangles and maybe windows, and then look at even more complicated features which are which are not rectangle like shapes. The whole premise of convolutional neural networks is that in this case, while I've specifically set the parameters or the filters, convolutional neural network will learn the set of filters in order to best do the classification or the clustering job at hand, right? So that's the whole idea. We want to learn these set of parameters. Learning of these parameters is the same as applying the same principles of backpropagation that you've been doing for multi-layer perceptrons. So having understood the building blocks and having seen a demo of edge detection, let's go ahead and do some calculations, some arithmetic. So you're given an image of, let's say, size n cross n and a filter of size f cross f. Then can you tell us what is the size of the output image? So for instance, in this case, n cross n is 4 cross 4, the filter is 3 cross 3, and the size of output is 2 cross 2. So can you tell in general, given n cross n and filter f cross f, what is the size of the output? It should be fairly trivial to see that this would be n minus f plus 1 times n minus f plus 1. You can just work it out by just moving the filter across the input image, and you will immediately see that this is n minus f plus 1 cross n minus f plus 1. So in general, you'd end up with output images of smaller dimension. Okay, a quick question for you at this point of time. Let's start with 32 cross 32 image. MNIST type datasets are of very similar shape, and you are repeatedly applying a 5 cross 5 filter. So after how many operations will you have a 1 cross 1 output or something similar to that? Assuming you paused and you worked out the problem. So you start with a 32 cross 32. I'll just use n and f as 5, and I look at n minus f plus 1. So in iteration number 1, or initially you had n equal to 32. After the first iteration, you'll have 32 minus 5, 27 plus 1, 28. Then for the next iteration, I have 28 minus 5, 23 plus 1, 24, and 24 minus 4, 20, 20 minus 4, 16, and so on and so forth. So what you might see is that you would have already observed that we are at each such operation, we're reducing the size of the output, right? Which is bad in some sense, but we'll come to that soon. So it's bad in the sense that we cannot go very deep with repeated convolutions, as the image size will reduce very quickly. And deep learning means going very deep in the network, right? Having a lot of layers. So we need to do something to sort of fix this problem. And another reason or another motivation for what I'm going to show you is the number of times certain pixels are being used, or the advantage that central pixels hold over the corner pixels. So if you look at the leftmost pixel, which is 3 in this image, how many times does the filter pass over it? Right? So you might see that the filter will pass over the leftmost image only once, right? But let's consider the central pixel 2 over here. So how many times does the filter pass over it? 1, and then it starts from this point 2, then it starts from this point 3, then it starts from this point 4, then it starts from this point 5, 6, 7, 8, and 9. So the middle pixel is used 9 times, whereas the corner pixels are used only once. So this is sort of unfair on the corner pixel also, right? Why should they have sort of lesser contribution or lesser importance, lesser multiplication, lesser number of times being used or multiplied by the filter? So we say that this problem is that the corner pixels are underutilized, and a simple way to mitigate this is to add a padding set of units, right? So this padding set of units is so you put in some additional pixels. Typically you just put the pixels of zeros, right? You basically pad the input image, and when you pad on all the sides. So if you had an n cross n image and you had a padding of p pixels, in this case p equal to 1, you'll have output image of n cross n, so n plus p cross n plus p, right? So the output image size is now n plus 2p times n plus 2p. So once you've done this padding, then this particular image will be used much more than it was previously. Now this particular image will be used 1, 2, and 3 and 4. So at least 4 times it's being used. Of course, not being used as much still as the central pixel, but it's better. If you were to increase the padding, this would get used as much as the inner pixel now, right? And the idea is now once after padding, you can apply the same convolutional operation on this padded image, and you can then get an output. So previously the output was a 2x2 matrix, but now the output is a 3x3 matrix, which makes sense because now the input has been changed from n to n plus 2p cross n cross n to n plus 2p cross n plus 2p, right? This particular slide just shows the padding operation. So you apply the filter to over the leftmost block, you get the first value, the second block you get the second value, and so on and so forth. So actually this is also introducing another concept which we have thus far not discussed about, which is known as strides. So if you see that this is skipping this, but the square which should have started from this point, right? It has instead jumped 2 points from this point to this point, and from this point to this point, right? So we have basically made a stride of 2. Jumped we've jumped 2 blocks instead of jumping 1 block. But the important thing here is to understand how padding works. Okay. Okay. This image gives another beautiful representation or visualization of padding with the convolution operation applied over it. And you see the original n plus n we have added now p equal to 2 pixel width padding, and thus you see an output image. So the input image was 1, 2, 3, 4, 5 plus 5, and the output is 1, 2, 3, 4, 5, 6, which is sort of unusual that the output is more than the input, but that's because we have added a lot of padding. The question for you at this point is that given a padding of p pixels, an n cross n image, and filter of f cross f, what is the output size? I am assuming you pause this and you think for a minute. So for n cross n, the size is n minus f plus 1. But if you change from n cross n to n plus 2p cross n plus 2p, this becomes n plus 2p minus f plus 1. That's the only change that you need to make. Fairly simple. And there is something known as same padding. So Keras and similar implementation have defined things like valid padding or same padding, etc., etc. Same padding means that the input image, and then you apply padding, and then you apply the filter, is the same size as the output image. So which means n plus 2p minus f plus 1 is the same as n, or which means that p equal to f minus 1 by 2 for same padding. So of course you'll see, you would have guessed by now that in this case f has to be an odd number. Coming to strides, now what you want to do is to sometimes subsample. You saw that if we consider all the pixel values, then you'll end up with the next output image also as a big image, right? You want to somehow reduce the number of parameters overall, and you want to basically reduce the computations. You skip some elements or some input pixels. Now one rationale behind that is that if the image has a lot of pixels, is a very huge image, and there is not a lot of local variation, then knowing about one particular pixel also tells you a lot about the next pixel, about the adjacent pixel. So you don't necessarily need to do that computation on the adjacent pixel also. And you generally also assume that if there are things like edges, etc., they are not really very thin. I mean, they're so thick enough that you'd still be able to detect them after subsampling or after applying strides. This image shows that you've applied a stride of 2. So you make a jump 2 places, and then from even in the vertical block you make a jump of 2 blocks, right? That's why this 5 cross 5 image and a 3 cross 3 filter, we get a 2 cross 2 output image. The question for you at this point is that given a padding of p pixels, an n cross n image, f cross f filter, and s stride, what is the output length? I'm assuming you have paused the video and thought through this. The answer is the floor of n plus 2p minus f. So n plus 2p minus f is anyway common, right? You've been seeing this earlier itself, and divided by s, because now you have a stride of s, so you're jumping through, and then you take a floor of it. So you take a floor because there'll be chances when you'll not be able to cover the entire spectrum because you are jumping every s pixel, so you'll not be able to cover the entire row or column, let's say. And then plus 1, which you have again been seeing earlier. So the only thing which has changed is this floor operation, because now you're making skipping every s pixels. There are other operations also which are very generally which are very commonly applied in convolutional neural network literature. One of them is called as pooling. So this is also a subsampling technique, and this is an interesting kind of an operation because it does not have any parameters associated with it. So you apply a pooling filter which just aggregates the input in that. So let's say if you applied a 3 cross 3 pooling filter, with this particular filter just tells me the max value which occurs. So that max will be 3. You apply that pooling filter here, you'll again get a 3. You apply a pooling filter again here, and you'll see that there are 2 3, so the max value is 3. Apply a pooling filter here and you get a 3. Applying a pooling filter here, you again get a 3. Applying a pooling filter again, you get a 3. Apply a pooling filter, max, get a 3. Max is 2 and max is 3, right? So you have, in a really simple, using a really simple function, you have subsampled the data, right? And you have created an output image which is smaller than the input image. And in practice, this is shown to be work well, and it also generalizes well because it is helping you to reduce the representation size. Similar to max pooling, there is an average pooling, which empirically I believe does not work as good as max pooling, but everything else is pretty much the same. So you just take the average of all the pixels in the filter area. Okay, so now we come to the concept of applying these filters when you have multiple channels. So thus far we had been having an input image, right? Which an input image means that it's only a single dimension, as in it has only a width and a height, right? It doesn't have a corresponding depth, right? But now we assume that there is a depth also, or in trivial sense, let's consider an input RGB image. So you have n pixels height, n pixels width, and C equal to 3 channels in this. So the way convolutional neural networks or filters are applied in this case is that you'll first have a filter for the red channel. Let's say that is f cross f. The filter for the remaining channel will also again be f cross f only. So you apply this whole operation, you apply the convolutional operation on this 5 by 5 image and a 3 cross 3 filter, and you'll get a n minus f plus 1 cross n minus f plus 1. So n was 5, f was 3, 5 minus 3, 2 plus 1, 3 cross 3 image you get. You do the same thing for a green filter, and you do a same thing for a blue filter, right? So in total you have obtained 9 such numbers now, right, based on your filter values. So your filter consists of 3 matrices of size 3 cross 3, right? So total your inputs have the number of parameters in your filter is 3 cross 3 cross 3, which is 27 numbers. The output that you get is 3 channel output of size 3 cross 3, but then the way you aggregate them is to add up all of these numbers to finally again get a 3 cross 3 matrix. So you add up the 0 comma 0 of each of the 3 output images that you get, and 1 0 comma 1 of all of these 3, so on and so forth. You'll finally get an image which is 3 cross 3, right? So when you apply a single filter, in this case, you should be very careful and see that the input was n cross C. So C channel C equal to 3. The filter has to have the same number of channels, because that's how you will be able to multiply each of them or apply the filter individually to each of the channel in the input. Once you do that, you will obtain C such images of size n minus f plus 1 cross n minus f plus 1. Then you aggregate or add all of the numbers, or basically just add these three matrices, and you'll get a single matrix of size n minus f plus 1 cross n minus f plus 1, right? So far so good. And the way then you apply the nonlinear activation function. So think of the operation that you've thus far done to be analogous to when you compute z. So you compute z equal to a times w transpose plus b. So, and after that you apply a nonlinear activation function. For convolutional neural networks, you're doing exactly the same, but the only difference is that instead of doing a times w transpose plus b to calculate z, you apply the convolution operation, and after that you'll get finally an image on top of which you add a bias, right? A bias would be added basically a single number which is added to each of the element in this array, and then you apply a nonlinear activation such as ReLU, right? So what we have seen thus far is an input image of n cross C, one filter of size f cross 3, and so 3 is here is basically C, right? Once you apply one such filter, you'll get an output or an activation output which is n minus f plus 1 times n minus f plus 1, and then you can apply multiple such filters. So in the edge detection case, we saw that there could be a vertical edge filter, there could be horizontal edge filter, there could be filter of which is trying to maybe look at slants, which is looking at 45 degree slants, which is looking at 135 degree slants, which is looking at some border pixels, or which is looking at certain features in one of the colors but not in the others, so on and so forth. So thus you want to have multiple such filters, and the number of filters that you have, so number of filters that you have over here would be the number of channels that you get after activation finally, right? Because then you'll get let's say the number of filters here is nf, right? So you'll get nf such images, and getting nf such images can be thought of as just an n cross c. Instead of that, we'll have n minus f plus 1 cross n minus f plus 1 times nf, right, after applying the activation functions. And after that, you can again repeatedly keep doing this operation. So you may also want to just confirm the understanding that the number of filters can be any number now. It need not be limited to 3, and then you apply the same set of filter for the next layer, which would be again some f cross the number of filters which you're using in the previous layer, right? So that would be the filter dimension for the next layer. So that's mostly what there is to convolutional neural networks. When you can dive deeper, you can do a lot of examples, you can work out with some good tutorials and some good problem statements. You could do things like cats versus dogs, but this is mostly all that is there to convolutional neural networks, at least in the basic sense. And one of the things you might want to do is to implement LeNet 5. This is again the network from Jan LeCun, and this is uh, trying to classify these images, right, or numbers. I just explain some of the steps in this and just present this as a case study. You have an input of size 32 cross 32. So the input size is already very clear in this 32 cross 32, and 32 cross 32 cross 1. Okay, let's just make that clear because it's a grayscale image, so no, only a single channel, which means that when you use filters when you use filters here, those filters also need to have only a single channel, right? So after those filters are used, so the filter size is not given here by the way. Once you use those filters, you get something like 6 output images of size 28 cross 28, right? So the question here is that what is the filter size, and assuming there is no padding and no strides, just to keep things simple for now, no padding, no strides, what is the filter size? Second, what is the number of filters being used in this layer? So if you could think for a minute, I'm now assuming you've already thought for a minute. Okay, so from an image of 32 cross 32, we want an image of 28 cross 28. N is 32 and n minus f plus 1 is 28, which just clarifies to you that f is going to be 5, right? And we've assumed that no padding and stride 1, so basically there is no additional stride, just to make things simple. And what is the number of such filters being used? You get that using this number. So there are 6 images that you get of size 28 cross 28. That 6 comes from 6 filters of size 5 cross 5 being used, right? Once that is being done, then they use something known as subsampling. We have already seen what is subsampling, right? Like we looked at things like pooling or strides, which could give you subsampling. The number of layers filters used in the first layer, I've already just gone over that. 6 number of filters are being used. So now you want to go from 6 cross 28 cross 28 to 6 cross 14 cross 14, which means that you're applying some operation to subsample the data. And what is being used in this case is a pool filter, right? So you apply pooling and then you go from 28 cross 28 to 14 cross 14. So what do you think is the size of the pool filter? So this pool filter is f equal to 2 and stride equal to 2. And you can verify this that when you put n equal to 28, f equal to 2. So 28 minus 2 is 26, divided by 2 is 13, and the floor of 13 is also 13, plus 1 is 14, right? So you 28 minus 2 divided by 2 is 13, plus 1 is 14, and thus you get 14 cross 14 images, and you retain the number of channels because we've not done anything with the number of channels. Next, you apply again a convolution operation. So you go from 6 images of 14 cross 14, or basically 14 cross 14 cross 6 channels, right? So if you have 6 channels in this particular image or input, what should be the filter size to get to a 10 cross 10 image, right? So the filter size, firstly you need to just ensure is that if we go back, the filter size here is n cross, the input is n cross c, the filter has to be f cross c, right? Because you need to multiply with the corresponding channels. So you will end up with 16 filters of size 5 cross 5 with stride 1. So from 14 cross 14, if you want to get to 10 cross 10, you want to 14 minus 5, 9 plus 1, 10. And each of these filters will also have 6 channels. So ideally this should have been 5 cross 5 cross 6. And that's how you'll be able to get through all the channels and then add up and get a single number. But then since you get 16 such images, it means that you have 16 such filters, right? After that you get an image of size 16 channels and 10 cross 10 image, and then again there is some sampling. So you go from 16 images or 16 channels of 10 cross 10 to 16 channels of 5 cross 5. You would have already figured out that the size of this pool is the same as the size of the previous pool filter, f equal to 2 and s equal to 2. At this point you have 16 cross 5 cross 5, which is 25 into 16, which is 400 numbers, right? So given this 400 numbers, you just flatten this out and then you connect to a fully corrected neural network. So this is now just a MLP now. This has 120 neurons, this has 84 neurons, and this is 10 neurons. The output layer has 10 neurons. So you connect these 400 numbers. You just think of this layer as 400 neuron numbers. You connect it to 120 neurons in the next layer, and then 84 and 10. Right. So this is how generally all convolutional neural networks end. They start with an image which is big and the number of channels is low. Gradually you keep on increasing the number of channels in the image, which means you use more and more filters, and you basically go from something which is tall and which has more width and height and less depth, to something which is which has really small width and height but has a lot of depth. And finally, so you then just flatten it out, and then you used fully connected layers, and that's how LeCun worked. And this was, if you run this on something like MNIST dataset, you'll see that even this very trivial looking or very simple looking network will perform really well. But this does have a lot of parameters, this convolutional neural networks. But one thing you need to see is that majority of those parameters are coming in from the final set of layers and not from the initial set of layers. Let's do a calculation for the number of parameters. Right, let's go by one. The first convolution is 6 filters of size 5 cross 5 cross 1 channel. So this is 6 filters, size 5 cross 5, 25 numbers in those, and 6 is 150 total numbers. Plus for each of the filter you have a corresponding bias, right? You add a B. So total 156 such numbers. Then you apply a max pooling. Does it have any number of parameters? No, because it's just picking up the max value or the average value in those regions in which you're applying the filter. Then you have a conv2. So 16 filters of size 5 cross 5 cross 6, because there were 6 channels. There were 6 channels here, right? So 16 times 5 times 5 times 6, plus for each of the filter you have a corresponding bias. So total 2416 params. And then you come to the fully connected one layer, right? So you have 400 parameters here, and you have, by the way, I skipped this subsampling because we've already seen that subsampling has no parameters. So this particular weight matrix, which connects this 400 numbers to this 120 numbers, would be a weight matrix of size 120 cross 400 plus the 120 biases which exist for the each of these nodes in this 120 in this particular layer. Similarly, the next layer will have 120 cross 84 size weight matrix plus 84 params, and finally 84 cross 10 plus 10 parameters, 10 parameters for the bias terms. So in total, this simple looking or this innocent looking network has 61,000 parameters. On a modern network or a modern computer, this shouldn't take you more than 2 minutes or so to train a fairly complicated, not a fairly complicated, an MNIST like network. But this just gives you an indication of the huge number of parameters that exist. But just look at these number of parameters in contrast to the number of parameters if we were to directly use MLPs, which I was showing initially that could be in billions, but this is just 61,000. A lot of modern neural network papers just keep on applying convolutional operation over and over. If you see, the convolution operations are generally fairly innocent in terms of the number of parameters, and that also makes sense because they have this property of local features which are translation invariant. So what that suggests is that if you're learning something in one part of the image, you can reuse that filter in any other part of the image, so you don't need to build something different for each part of the image. That saves you a lot of memory. With this, I'll end this particular lecture. We'll hopefully have a tutorial session or a discussion session where we talk about some of these different modern models like LeCun, AlexNet, VGG16, and different ways in which CNNs are being trained. You could of course train from scratch like we did for the MLP, but one of the most important advancement in terms of CNNs has been the whole concept of transfer learning. So essentially what that says is, let's say that there is a very complicated neural network which has convolutional neural network which has learned some very beautiful features. Let's say I'm applying this on images and I've learned something on the Imagenet. Now I'm doing something different. I am doing a really small task, but I don't have a lot of label data. So this could be, just classifying something which is not there in ImageNet. This could be just classifying certain breeds of plants in a campus. Now we can leverage all the data in ImageNet, and we already know that there is, all the beautiful features have been learned from that. These features could be edges or different types of shapes, etc., etc. Now we can use all of those features and just fine tune them for our own task. So which would mean that we preserve all of these layers and their weights, because these are essentially all the just features, and only when you get to the dense component or the fully connected component, you allow the fine tuning of the weights. So basically you freeze the initial part of the network and then you still allow some training in the last part of the network. That could also depend on whether you only allow training in the last layer or last one or two layers or how many layers. But that's the whole idea, that you don't need to learn features again because you've learned them from a much larger data set. All you're trying to see is that how those features occur in your data and what is the significance of each of those features in your specific classification task. The other interesting things about CNNs is how to visualize them and how to understand what are the filters being learned. Again, this is an advanced topic. We may or may not cover this in interest of time, but if we do, it will probably be a TA session. With this, we'll end today's lecture and the discussion on CNNs.